Hey everyone, and welcome to this explainer on continuous probability. If you've ever found yourself wondering exactly how analysts predict elevator wait times or how they map out probabilities when there are literally an infinite number of possible outcomes, well, you are absolutely in the right place. Today, we're setting the stage to decode some seemingly complex mathematical concepts that actually govern the random events in our everyday lives. We're going to be looking at 3 distinct flavors of predictability. So, here is our roadmap for today. We'll start with beyond discrete, continuous probability. Then we'll cover the almighty normal distribution, followed by standardizing with z-scores. After that, we've got the uniform distribution explained, and we'll wrap things up with tracking time exponential distribution. All right, let's dive right into our first section, beyond discrete, continuous probability. You know, the difference between these two worlds is actually pretty huge. Discrete probability is all about those exact, countable outcomes, which is why we can just easily organize it into a table format. But continuous probability, that deals with measurements that can be broken down infinitely, things like time or weight. Because of that infinite nature, we can't just slap it into a simple table. We have to use an equation or a formula instead. And get this, here is a totally mind-bending fact. In a continuous distribution, the probability of hitting one exact, infinitely precise value is actually 0. No way around it, we have to look at ranges instead. Okay, moving right along to our first major category, the almighty normal distribution. Also known as the Gaussian distribution, it's easily the most ubiquitous continuous model out there. And what's honestly fascinating is that this entire massive distribution is completely controlled by just 2 little parameters. First, we have the mean, represented by the Greek letter mu. The mean simply dictates the center location of the graph. Shifting its value literally just slides the center of our normal curve left or right. Second, we have the standard deviation, represented by sigma. This one determines the height and width. A smaller standard deviation makes the curve much steeper and tighter, while a larger one flattens it out, making it broad. Let's quickly run through its core traits. The normal distribution curve is perfectly symmetric and bell-shaped. Because of that perfect symmetry, the mean, median, and mode all sit exactly at the same center point and are perfectly equal. The curve is also asymptotic, which just means the tails stretch out forever and never actually touch the x-axis. Finally, and this is crucial, despite stretching out infinitely, the total area under this curve is exactly 1.00, or 100%. Now, knowing those properties unlocks something called the empirical rule, and it starts right here. For any normal distribution, a very reliable 68% of your data will fall within just 1 standard deviation of the mean. If we cast our net just a little bit wider, out to 2 standard deviations, that number jumps up to capture approximately 95% of all values. And to complete the pattern, if we step out to 3 standard deviations, a massive 99.7% of our data is captured. In the chaotic, messy real world, having that level of predictability is incredibly powerful. Which brings us to our next section, standardizing with z-scores. Because think about it, how do we actually calculate distinct probabilities when every single data set has a different mean and standard deviation? We obviously can't have a unique table for every curve in existence. So the solution is the z-score formula. It's a real game changer. By taking our specific observation, subtracting the mean, and dividing by the standard deviation, we mathematically shift the center of our data right to 0. This standardizes our particular observation so it fits perfectly onto one universal master probability table. Once you've got that standardized z-score, the z-table literally does the rest of the work. It's just a logical 3-step process. Match your first digits to the correct row, find the second decimal in the column, and exactly where they intersect, boom, you find your precise probability. It's like unlocking a puzzle. All right, let's shift gears to our second flavor, the uniform distribution explained. This is the rectangular probability distribution, where every outcome over a specific range has the exact same height. Let's apply this to a real-world mystery. Say you arrive at a building, press the button, and the elevator arrives uniformly anywhere between 0 and 40 seconds. We want to figure out the exact odds that the elevator takes less than 15 seconds to arrive. Since the total area absolutely must equal 100%, finding the height of our probability rectangle is just 1 divided by our total time interval. In this case, we drop our 0 and 40-second interval values into the formula. And as we solve that pretty simple fraction, we see the mathematical function gives us a consistent rectangular height of exactly 1 over 40, which equals 0.025. So 0.025 is our constant probability height across the entire 40-second wait. Now, to find our answer, we just look at the probability ratio. Dividing our target 15-second window by the 40-second total reveals a precise 0.375. Yep, that's a 37.5% chance that your elevator arrives in under 15 seconds. Finally, let's explore our third and final flavor, tracking time exponential distribution. Also known as the negative exponential distribution, this one is specifically used to measure the time that elapses between two occurrences of an event. And this model is incredibly useful out in the wild. Think about situations where you need to track intervals, like the time required to complete a survey questionnaire, the time between vehicle arrivals at a busy toll booth, or even physical spans, like the distance between major defects on a stretch of highway. Let's look at a practical, everyday business example. At Joe Muff Mufflers and Headers, a mechanic can install an average of 3 new mufflers per hour, and we happen to know this service time is exponentially distributed. So, what are the exact odds that a single job takes half an hour or less? Now, the exponential formula might look a little bit intimidating at first glance, but it's really just pitting our target time against our average rate. We take our average of 3 mufflers an hour, our target of half an hour, and plug them into the function, which is driven by Euler's number, E. When we let the math crunch those variables, taking 1 minus e to the power of negative 3 times 0.5, we get our definitive answer. There is a 77.687% chance that the mechanic wraps up the installation in exactly half an hour or less. And that, folks, is how these 3 distinct mathematical models govern the seemingly random world around us. By understanding their unique rules, we can actually bring order to the unpredictable. So, the next time you're waiting for an elevator or just wondering when the next car will pass by, ask yourself, are you just waiting? Or are you actually living inside a probability curve?